Hi everyone. So now let's talk about the last part of the first half of Econ 4a, instrumental variables. So let's begin with a simple regression before we talk about the general vector forms of the instrumental variable. Let's start with a simple regression model like this guy here. Okay. So if the OLS1 fails and x is correlated with the error term u, then we say x is endogenous and the OLS estimators are inconsistent. We know both the estimates for the intercept term, beta 0 hat, and for the slope term will be biased or will be inconsistent. So one solution we learned in undergrads is we can find an instrumental variable, z. And z needs to meet the two conditions. The first one is it's uncorrelated with the error term, that's exogeneity. And also, z needs to be correlated with x, that's we call relevance. The two conditions implied excludability, which means z can only affect y through x. And therefore, in some literature, people will call an instrumental variable excluded restrictions. Right, so an instrumental variable sometimes is called an excluded restriction in some literature. Okay, let's see why these two conditions imply excludability. So we have x affects y, and also the error term also affects y, but unfortunately there's some correlation between x and u. If we have an instrumental variable that is uncorrelated with u, so there's no correlation here, no, but it affects x, then we know z affect y only through x, right? Okay. So that's why we say the two conditions implies excludability. Okay. And note that relevance can be tested, right? It's very easy to test whether z and x are correlated. You just simply run a regression. However, exogeneity can only be taken by faith because there's no way we can observe the error term. So we cannot test the exogeneity assumption. Okay. Okay, so if we write down the covariance z over y, then plug in y equals beta 0 plus beta 1x plus u, because we know z and u, the covariance between z and u is 0, so we only have beta 1 times covariance z and x. Because covariance z and x is not 0, the relevance condition, we can move that to the left-hand side here. And therefore, we know beta 1 equals covariance zy over covariance zx. And by the method of moment or analog principle, we can use simple covariance to obtain a consistent estimate here, right? And that's the IV estimator we have. And it's very easy to show it is consistent. However, the IV estimator is never unbiased. It is always biased in the finite sample. So why is that? Note that because there's U, there's still X here, right? So in the finite sample, if X is endogenous and correlated with U, there will be some correlation between X and U here. And in fact, even if we are willing to assume a stronger condition, a stronger exogeneity condition that the conditional mean of U given Z is 0, the IV estimator is still biased. In fact, unbiasedness needs the conditional mean of the error term given both X and Z to be 0. However, if the conditional mean of U given X is 0, then we can just run an OLS. We don't need an IV, we don't need an instrument. And so the bias disappears only as the sample size grows to infinity. So it is consistent, but it is biased in the finite sample. So we need a large sample to implement an instrumental variable estimation. Otherwise, the finite sample properties of IV estimators could be pretty bad. Unfortunately, it's difficult to know how large is large enough. Okay, that's like all the problem we have in asymptotic analysis. It's always an empirical question, and you may be able to do some simulation to deal with that. But in general, we don't have a theoretical prediction of how large is a sample size large enough. So what if we have more than one instrument? For example, we have two valid instruments, Z1 and Z2. Clearly, we can only use Z1 or we can use only Z1 or Z2 as an instrument. But intuitively, you can imagine a more efficient way is to use both Z1 and Z2. And that's something we call the two-stage least squares estimation. If both Z1 and Z2 are valid instruments, the IV estimator using Z1 as instrument, the IV estimator using Z2 as estimator, and the two-stage least square estimator that use both Z1 and Z2 are all consistent. So in principle, these estimates from the three different estimators should be the same. And in fact, we can test that whether they are indeed the same. If we cannot reject that they are different, then we can say that both Z1 and Z2 are indeed valid instruments. And that's something we call over-identification test. Okay, so the idea is say, well, if Z1 is a valid instrument, Z2 is a valid instrument, then using either Z1 or using either Z2 or combine them, you should get the same results. Okay. However, nowadays people don't really like to use over-identification tests that much because for two reasons. First of all, it is possible that your estimates, both Z1 and Z2 are endogenous, but they are biased in the same direction. So your IV estimates from Z1 and Z2 are the same, but they are both wrong. Second, later we are going to talk about local average treatment effects, and that is very important properties in an IV framework, right? So that's basically saying you could get very different IV estimates from two different instruments because they capture different treatment effects. Okay, because in general, remember that beta could be a random variable beta I, right? So maybe some people are, in the data, maybe some people are more affected by Z1, some other people are more affected by Z2, but people who are affected by Z1 has a beta I that is different from people who are affected by Z2. Okay, so even if you get different estimates, that doesn't necessarily imply that your instruments are endogenous. And therefore, nowadays people don't really like doing over-identification tests, and that's why I'm not going to talk about details of different type of over-identification tests. Okay. So just to remember, if you see something over-identification test, that means they compare whether the IV estimates are similar across different instruments. So you needed to have more than one instrument in order to do that kind of over-identification test. Okay, so if we want to use both Z1 and Z2 to form a two-stage least square estimator, what is the best linear combination you can get? Well, we already learned that, right? We can use a linear projection. By definition, the linear projection is the best linear combination of the two or a bunch of a vector of variables. So the linear projection is a function of Z1 and Z2. If Z1 and Z2 both are uncorrelated with the error term, then the linear projection must be uncorrelated with the error term as well. Right. So therefore, we can use the linear projection as an instrument. How to estimate the linear projection then? Well, we know we can just use the OLS to estimate the linear projection, right? The OLS always consistently estimate the linear projection. Okay, and so we can have this one. If you request your endogenous variable x on instrument Z1 and Z2, and the predict value, and get the predict value x hat, and we can use x hat as an instrument. And if you plug in x hat into the IV estimator, so you replace z by x hat, we have our two-stage least square estimator. Again, the two-stage least square estimator is consistent but always biased in the finite sample. Here, it's also very clear to see, because y is a function of u, right? There's u in y. And x hat is a function of x. X hat is a function of z and this delta hat. But delta hat is a function of x, so u and delta hat are actually correlated in the finite sample. So that's why IV estimators are never unbiased in the finite sample when instruments are needed. Right? If your x is endogenous, then you need the IV. But because x also forms, because this like a delta hat is also a function of x, and x is correlated with the error term, so your IV or two-stage least square estimators are never unbiased in finite sample. Okay, so note that we can replace xi minus x bar here by xi hat minus x hat bar. They are actually the same. The reason is because we can rewrite xi as the predict value xi hat and the residual ri hat. And obviously xi hat and ri hats are orthogonal. That's the OLS or linear projection first order condition. Okay. So I mean, that's just first order condition, but why do we want to rewrite that way? Well, because if we rewrite that way, we know we can get the two-stage least square by regressing y on intercept term and the x hat. And that's how we get the name of two-stage least square, and this is what we call the second stage regression. Traditionally, in the past, when we don't have good software like Stata, that's how people implement two-stage least square. They actually run two regression, the first stage, and then they run the second stage. Nowadays, you don't have to do that in Stata or in software, in like modern software. Another thing here, because we know we can get the two-stage least square from regressing y on x hat, intuitively you can think about we use an instrument z to throw out endogenous part of x, right? Because xi hat is a function of z, so we only keep xi hat, but we drop all the endogenous part of x, those residual here, we just throw them away. We just threw this endogenous variation away. We just use exogenous or good part of variation of x. Right? So intuitively, we use the instrument Z to pick up the good variation and drop the or throw away the endogenous variation of x. Okay. So some more terminology. This thing, so the original model y equals beta x plus u is something we call the structural model. That means it is the economical model, and those parameters or coefficients, they do have economic meanings. For example, if you request income on years of education, then beta is the return to education. And if you plug in the first stage here, so you replace x by z, then we get something we call reduced form. Okay, reduced form is very, very important in the IV framework. Okay, so let's see. Next. Okay, so first of all, notice that you can rewrite your IV estimator as this is the reduced form, right? This is from regressing y on z, and the first stage, this is from regressing x on z. Right, so you can see that the IV or the two-stage least square estimate in general is the ratio of reduced form over the first stage. Okay. Okay, so in practice, a very important and a good robustness check is to run a reduced form regression to see if the instrument indeed predicts the outcome variable. Okay, so I put a quotation there because we know if our assumption of exogeneity is right, then z only affects y through x, right? So that's not really predict. But we want to check whether there is indeed an empirical relationship between z and y. The reason is we are going to talk about the weak IV problem later, but but if you look at the IV estimate here, right, you may have a very large and perhaps statistically significant IV estimator or IV estimates just because you have a very tiny small first stage, right? So IV could be very, very big if your first stage is very, very small, right? But that's going to be a problem because we know a good instrument actually needed to be strongly correlated with the endogenous variable, right? So a good instrument needed to be exogenous but also very relevant. But if you have a large IV estimate because of small first stage, that's going to be a problem, right? And we don't want to trust such estimates. So one way to avoid that is to also look at the reduced form, right? If you look at the reduced form, there is strong relationship, then you can be sure that your IV estimate is not driven by small first stage. Okay. Another thing, the two-stage least square estimate with only one instrument is numerically identical to an IV estimator. And in fact, in the literature, we don't really distinguish the term. You can say two-stage least square, you can say IV estimate. Another important thing, the instruments, another important situation that people will use instruments is to fix or to correct measurement error. Okay, measurement error often causes downward bias in the OLS estimates, but you can use instrument to fix that. So one example is like income, right? So usually if I want to look at, say, the effects of income on leisure, for example, if I request leisure on my personal income, okay, sorry. So let's say I want to look at the household income, the effect of household income on household leisure. I request household leisure on household income. But if I have income from household income reported by the husband and the household income reported by the wife, then instead of using only one or the average of the two reported income, one way you can do is to use, say, husband's reported household income as an instrument for the wife's reports household income. And that actually can fix some reporting or measurement error